The size of the nucleus. Rutherford estimated the size of the nucleus in his famous gold foil experiment. He took advantage of the conservation of energy. He assumed a head-on collision between an alpha particle and a gold nucleus. At the point of closest approach, that is, at the radius of the nucleus, all of the kinetic energy would be transformed into electrical potential energy. Taking advantage of that, he was able to calculate the distance to be 3.2 times 10 to the negative 14 meters. Additional experiments by other researchers generalized the radius of a nucleus for that of any nucleus based on its atomic mass. The result was the following formula. R equals R naught times a to the 1/3, where R naught is 1.2 times 10 to the negative 15 meters. Let's do some size comparisons. So what we've just learned is that nuclei have radii in the range of 10 to the negative 15 meters, also known as a femtometer, or the Fermi, named after famous Enrico Fermi, who was responsible for the first self-sustaining critical nuclear reaction. Now, by comparison, atoms have radii on the order of 10 to the negative 10 meters, so you can see just how small the nucleus is. What's also really amazing is that the charge on the proton is exactly the same as the charge on the electron, even though the proton is 1,836 times more massive. Nuclear energy levels. Just like atoms, nuclei also have energy levels. Electrons were described both by the Bohr model and the Schrödinger equation as being in well-defined energy states. When the electrons moved between these states, they either absorbed or emitted a photon depending on whether they moved to a higher or lower energy level. These photons in atomic transitions can be in the infrared, visible, ultraviolet, or even X-ray areas of the electromagnetic spectrum. The structure depended mostly on the attractive Coulomb force between the nucleus and the electrons, and a slight repulsive force between the electrons. Atomic energy levels are complex, but nuclear energy levels are more complex. The reason? There are two competing forces, not just the electromagnetic force, but also the strong force. The electromagnetic force, or Coulomb force, as you recall, is strongly repulsive between like charges, which would be the case for protons, and drops off as the inverse square of the distance between the particles. The strong nuclear force provides the attractive force between nucleons. It counteracts the repulsive Coulomb force between the protons to keep the nucleus together. This strong force acts only over a distance of about 1 femtometer, about the size of the nucleus. It increases in strength as the nucleons get further away, but only up to about 1 femtometer. There are, of course, two other forces. One is the weak nuclear force. This one is responsible for radioactive decay and converts neutrons to protons. The other force is the gravitational force, but this is insignificant at the scale of the nucleus when compared to the other forces. The results of these competing forces, the strong and the Coulomb, creates a more complex energy level scheme than that of the atom. But just like the electron energy levels in the atom, the nucleons can move between energy levels. And when this occurs, very high energy photons, gamma rays, are emitted or absorbed.